Okay, so I've spared you all the trouble of watching me sort through a massive pile of resistors. My resistor pack came from Banggood. Uh, and it's nice to have a lot of values, but maybe a fewer more common values would have been more manageable. In any case, see my cheating there. In any case, what we need is, we're also calling for 4.7 volt diode. So let's see if I may not have one, but that would be okay. Sometimes I don't have the 1.8K calls for, but sometimes it's okay to use what's close at hand. Because remember, you can adjust the voltage. Doesn't it look so good? For 4 volt 7. 7 volt. I'm not going to be able to read that, but let's grab one of the Zenas. And we can put the rest to the side. Excuse me. The other thing we need is a transistor. I don't have the specific transistor he's looking for, a BC548. This is a BC337. Should work just fine. And I also have a fairly generic, I don't know what this is, one in 1007 diode. That should be sufficient to build this circuit. So we'll get going. So this part is probably going to be fairly boring. I might try my skills at editing and fast forward through the entire thing. Let's plan this out then. First of all, we need power. I suppose we can use color appropriate jumpers for power from op-amp. Pin 8, 1, 2, 3, 4, 5, 6, 7, 8. Should probably check that. And I'm back. Brought with me a screwdriver, which should hopefully allow me to trim this thing. Yeah, that seems to work. And a lead. And what we can do, just because we're lazy and we don't like to hold our meter probes all over the place. And we should be on volts. I should actually turn this upside down. No, you can see it better this way. Yeah. Sometimes I forget how I've organized the setup here. Let's run a couple of tests. We have 13.5 volts. Let's confirm. That might explain something. Oh, no, that's negative. Well, that might explain some things. There is no voltage. 2.5. It's this thing again. These aren't great. Where did I had a yes. Well, let's do violence to our setup here. Just a old cheapo. Should probably turn off the power, and I'm just gonna trim a whole bunch of this off. Leave the end on for fun and games and profit or something. Yeah, this board wasn't actually necessarily the best buy, but okay. I didn't manage to get the other end off. Okay, let's see if that works now. 13.5. 13.5. We're in business. Ooh. Huh. Fascinating. I don't know if you can see this. Maybe I can organize for this to become visible. Let me look for a plug. Bear with me in this chaos. Oh, look, it's sunny dark. And I touch the... still not visible. And I touch the heatsink of the MOSFET. The LED comes on. Very dim. Probably got too big a resistor in the circuit. Okay, let's see, why aren't we working? Our reference voltage, what is our reference voltage? On the other end of the Xena, 13.5. That would imply the transistor is off, so let's turn our transistor on. We can force it on with our 10K resistor. 0.8. I got the wrong transistor here. Or I've got diode the wrong way around. I might have to diode the wrong way around. Oops. Let's just turn around, see what happens. Where did I have it connected? Okay. Nah, it'll probably be worse now. 4.5. Yes, I had the diode the wrong way around. Of course, there's a reverse breakdown on your Xena that causes your set point. Okay, so now we've got a set point. The transistor should latch on, maybe not. No, it's gone off again. So what it might do to see is what's the other set point. That's I think I see what I did wrong here. Let's kill the power. Yes. This, ladies and gentlemen, is why you never thought on anything on the first take, I guess. So I generated a nice, and in fact let's measure it for the sake of, fun and games. Nice sort of reference voltage, which is 10.5 volts. That's definitely not going to work out well for us. Let's play with the voltage before we connect to our op-amp. 10.6, 10.7, going the wrong way. Let's go down. These trim pots, you can turn them forever. So we want it at 13.5 volts. Actually, let's rather do a calibration here. So we drop that's our current. So let's go for 11 volt cutout. So if I set the 10.8, close enough. The 4.5 volt reference we need to drop below in order to cut out here. So I'm just going to set this to about 4.5 here. Okay, done. And now we should take our reference and actually connect it to the op-amp, that'll work much better. Much better. There's our reference. So, I'm forcing the transistor on, but the output may still be low. So let's just tweak our output up. That's current. Let's go to about 12 volts. Confirm that for you. We got 11.8. Either my meter's under reading or my bench power supply's wrong. Anyway, be that as it may, we've got 4.9. 4.9 on pin 3, which is of course our positive, against a reference of 4.4. So we would expect pin 1 to be high, and pin 1 is not high. We've probably blown out the chip or something. Let's just take a measurement there. We've got 12 volts on one side. Oh, that's weird. 11 volts. 12 volts. No, 12 volts on one side. And we should have 0 on pin 4. Yeah, did I get that right? We can just go back to this pin 4. Yep, that looks reasonable, I guess. I don't know. So, if maybe we're just pulling the output down. So we would expect on the leg of this resistor high output. We're not getting that. Why? Are you not working for me, little LM358? Are you indeed an LM358? If I stick my head here, LM358P. Well, let's measure on the actual chip. 4.6, 4.9. In my math, 4.6 is greater than 4.9. 4.9 is greater than 4.6. Multiplied by the gain, I would expect this to swing high. Let's just disconnect the load. Not that a 10K should be pulling us down. No, it's not. Do I have a dug op-amp? Excuse me, I have a bit of a cough, as you no doubt notice. My ground is definitely ground, and my positive is definitely positive, and my chip is not getting hot. Let us consider for a moment the wrong buttons. The other pin, the other op-amp on this chip. Op-amp out should be pin 7, according to my datasheet, which I just looked up. It's floating at about 1.3 volts. Inputs are floating. 0.9 volts, 0.8. It's floating. It's all over the place. What we could do is we could grab another couple of resistors and just stick some voltage into that. It's just which one is positive, which one is negative. In minus is pin 6, in plus is okay. In minus can go to negative, and plus can go to what value is this resistor? Red, invisible orange. I have somewhere a little kit I bought, also purchased on Vanguard. Not accurate, but it can be used in a case like this to just get a general. Works better if you like. Don't know if you can see that. 0 ohms. Well, let's not use that the resistor. Just take a 2K. I mean, they're high impedance inputs. I could theoretically just short them. It's not the greatest of kits. 2K. 0.1 microhenries. A bit disturbing. Excuse me. While I cough my lungs out. Ooh, don't short them together. Let's. Oh, of course. I am confused by the fact that I never set up things like this. Let's kill the power before we cook something. That is to positive, that's correct. That is to positive, that's... No, it's right, it's right. Oh. Well, anyway. For a moment I thought I'd connected negative and negative. But anyway, let's go for it. Now I forget what it's doing. Pin 7 is out, pin 2 is minus, pin 1 is plus. So let's just connect plus to... Ooh! That's fascinating. I'm pretty sure I've wired this thing wrong. 48231. Well, that's not expected. LM358P. 358P. Pin 1. You're all gonna laugh at me when you find out what I've done wrong. But then again, for all intents and purposes, I've been out of the game for a little while. No, pin 1 is output. How is connecting that affecting the first op amp? Pin 8 is positive. 1, 2, 3, 1. Especially since I've disconnected one side of... I haven't disconnected pin 1. Disconnected it from the BC337 circuit so that the voltage remains stable. Pin 8. I can't count. That's my problem. I can't count. Okay. Much better. We've powered the op amp now. Okay, so we've got a voltage of 4.97 on pin 3. We've got a voltage of... Oh, can't see that because I need to hide this guy. 4.97 on pin 3. On pin 2 we've got 11 volts. It's latched off. Shut up. 4.7. So theoretically, if I were to drop the voltage down a bit, it should turn off. It does. It does at a voltage of 10.2 volts. Bit low. Just that. And if I were to turn it back up, sort of oscillates on and off until we get a bit high. So there's a little bit... it was never designed to run in that mode. Anyway, the problem is, and it's latched on, and then it drops out. Seems to be some sort of time constant there. Or my power supply might not be stable. Well, pardon the clips and the bangs while I pull out a... In fact, I think I've got a better arbitrary size capacitor somewhere. Here's an arbitrary sized capacitor. It's 35 volts, 220 microfarads. Should be arbitrary enough for anyone. We connect it the right way so it doesn't blow up in my fingers. And let's see if that stabilizes things. Nope. We die down quite quickly. Maybe I need a little bit of sort of decoupling on the reference voltages. Ah. But that's what happened when you never opened it. Another arbitrary sized capacitor. See how scientific we are here. Reference voltage is this pin. Oh, this is connected. Ground. Okay, let's reset, see if it's stable. Aha. So what's probably happening here is this circuit's designed to run off a battery. That's the original designer left off all the decoupling capacitors. And basically what's happening is my switching power supply has a switching frequency. And it may just be possible the voltage dips in a way that's not visible on my meter, but would be visible on the scope. Oh no, it timed out. Okay, fair enough. That explanation's obviously wrong. Let's do it. How long does that take? Tell you a story of one of my friends who did something quite embarrassing on a stage once, but probably won't. So we're still 4.6 as opposed to 4. Ooh, that's interesting. Maybe the difference is my output is low and it will latch off. Output staying low. 4.65 and output will stay low because we're latched. Let's go up in voltage to about something more reasonable, 13.4. All it takes is a minor interruption in the output and the circuit will latch off. What we can do while we wait for it to latch off is we can show this again. And we can go to, yeah. So you can read in his description how it works, but basically what happens is when you cut out this transistor by dropping the output, basically the voltage on this pin will float to the supply voltage because there's no real path except for a tiny bit of leakage to cause the Zener diode to avalanche and basically set the voltage. So this point here becomes 13 point, you can see it, 13, at the moment it's, I'm sorting bits together, it did go off. This point here becomes 13.4 volts. Now, the switch here, I forget you can't see me pointing, will basically switch the transistor on, which will give us a voltage on the reference point of 4.5. That gets compared with the output of our basically divider here, which is this point here, which is 5 volts, 5.5 volts. Because 5 volts is bigger than 4.5 volts. The output should go on, and this should, in theory, hold the transistor on. If at any point you interrupt this, because this is never 4.5 volts again, the circuit's latched. So the question is, why would the op-amp be dropping off? Maybe, okay. Hold on while I secure my power supply.